Hi everyone, till today we have completed exercise 1.1 till question number 8. Question number 9 is your homework as it is same as the previous questions. Now let us start question number 10. Give an example of a relation which is transitive but neither reflexive and nor symmetric. So we need to find a relation which satisfies this condition. Okay. So let us take R is equals to all the order pair AB such that A is less than B. Now here we want a relation which is transitive but neither reflexive nor symmetric, right? So if we say A, let us take any A from our set, okay? Now we can never say that A is less than B, right? Therefore AA does not belongs to R. So here R is not reflexive. Okay, that's why I have chosen here less than. Suppose if the question is like this, find the relation which is transitive and reflexive. If I want to make this reflexive, then I have to add here equality sign. But as here in our question, we want to find a relation which is not reflexive. That's why we have written here A is less than B. Okay. So here this relation is not reflexive. Now let us see the symmetricity. So if we say that 2 is less than 3, but we know that 3 is not less than 2. So if A is less than B, then B cannot be less than A. Then B will be greater than A, and therefore the relation is not symmetric. Now we want to check its transitivity. For transitivity, if AB belongs to R and BC belongs to R. Now if AB belongs to R, what does it mean? Then A is less than B. Okay. Whatever order pairs are there in our relation, then that order pair will satisfy the condition of the relation. So here our condition is A is less than B. So AB belongs to R implies A is less than B. BC belongs to R implies B is less than C. Now if A is less than B and B is less than C, then we can say that A is less than C. So we can understand this example by taking particular values of A, B and C. If we take A equals to 1, B is 2 and C is 3. So 1 is less than 2? Yes. 2 is less than 3? Yes. Therefore 1 is less than 3. Okay, so this is very trivial, obvious. So if AB belongs to R and BC belongs to R in this relation, then AC must be in R and therefore R is transitive. So this is the relation which is transitive but neither reflexive nor symmetric. Let us move on the next sum. Okay, so same sub question number 3. Now we will find a relation which is reflexive and symmetric but not transitive. Okay, so let A is equals to 1, 2, 3. See here, whenever you want to find some relation, you have two ways. Either you write down in a listing method, you simply write down few order pairs which satisfy our condition, or else you can give the generalization that we have done in the previous sum, that A is less than B. Okay, so here we are taking our R in a listing form. Okay, now we have chosen our A is equals to 1, 2, 3. Now as we want our relation reflexive, we have to insert 1, 1, 2, 2 and 3, 3 into this relation. Then only it will be reflexive. Now for symmetricity, if you are taking 1, 2, then you must have to take 2, 1, right? If you are again adding 1, 3, then you have to add 3, 1. So if you have 2, 3, suppose you are inserting 2, 3 in this relation, then you must have to insert, yes, right, 3, 2 into the relation. So right now we are beginning with this relation. So obviously this relation is reflexive as it contains 1, 1, 2, 2 and 3, 3. Now will it be symmetric? Yes. Why? Because if we take 1, 2, so it's reverse, 2, 1 is there. If we are taking 1, 3, then again 3, 1 is there. Okay. So this relation is reflexive and symmetric. Now what about transitive? So here if we select 1, 2, right, and you select 2, 1, then 1, 1 belongs to R. So for this pair it is transitive. Now to check whether it is, let us choose one other pair, that is 1, 3 and 3, 1. So again 1, 3 and 3, 1. So 1, 1 is there. Now you consider another way. You consider first order pair is 3, 1. Okay. And one more order pair which should start from 1. So with the 3, 1 we are considering 1, 2. So 3, 1 belongs to R, 1, 2 belongs to R. But 3, 2 does not belongs to R. That means the relation is not transitive. So to check transitivity, okay, you can also take A1, B2 or 3, right? So you can take like A1, 2. Then you consider the other pair which start from 2, okay, or 3. So we have already discussed this part, and therefore we can say that here R is not transitive. So let us move on the next sum. Now give the relation which is reflexive and transitive but not symmetric. So it should be reflexive and transitive but not symmetric. So for reflexivity, again we are considering our set A. So let's set A equals to 1, 2, 3. If it is reflexive, then it should contain 1, 1, 2, 2 and 3, 3. So let us insert those order pair, that is 1, 1, 2, 2 and 3, 3 here. Okay. Now it should be transitive. So if I am taking here 1, 2, we will not consider 2, 1. Why? If we are considering 2, 1, then it will be symmetric. But we want our relation should not be symmetric. So let us take 1, 2 and 2, 3. Okay, now it should be transitive. So when we are inserting 1, 2 and 2, 3, we must have to insert 1, 3 inside this relation. Okay. So now this is the relation which we want, which is reflexive, transitive but not symmetric. Now in next sum we want to find relation which is symmetric and transitive but not reflexive. So this is your homework. See, it should not be reflexive. So either you skip 1, 1 or 2, 2 or 3, 3. Or you can also skip 2 order pairs. Okay. Or maybe all 3, right? So this is your homework. I have already given you the hint, but next remaining parts you have to solve as a homework. Okay, now question number 11. Show that the relation R in the set A of points in a plane given by all the relation R will contain all the order pair PQ such that distance of the point P from the origin is same as the distance of the point Q from the origin. That means P and Q should both be at the same distance from the origin. Is an equivalence relation. Now recall that what is equivalence relation? If the relation is symmetric, reflexive as well as transitive. Now further show that the set of all the points related to a point P which is not origin is the circle passing through P with origin as the center. So that we will discuss later on. First of all, let us solve the first part of the problem. Let us consider R is equals to PQ, where distance of point P from the origin is the same as the distance of point Q from the origin. So let origin is equals to O. So here what should satisfy? That OP, that is distance of O from P, should equals to distance of O from point Q. Okay, so in a simple way we have written our relation R. Condition of the relation is if OP equals to OQ, then only PQ belongs to R. So let us move further. So let us check reflexivity. Since point P and point P are same, distance of point P from the origin is equals to distance of point P from the origin. That means P comma P belongs to R. Hence R is reflexive. Now for symmetricity. Now if distance of point P from the origin is equals to distance of point Q from the origin, then we can also write the same thing in a reverse order. That is distance of point Q from the origin is equals to distance of point P from the origin. Hence, if PQ belongs to R, then QP belongs to R. It means that R is symmetric. Now transitivity. If distance of point P from the origin is equals to distance of point Q from the origin and distance of Q from the origin is equals to distance of point S from the origin, then from this first line we can say that OP equals to OQ. Here from second line we can say that OQ equals to OS. So if OP equals to OQ is equals to OS, we can directly say that OP is equals to OS. In words we can say that distance of point P from the origin is equals to distance of point S from the origin. And therefore here if PQ belongs to R and QS belongs to R, we can say that PS belongs to R and R is a symmetric. R is a transitive. So since R is reflexive, symmetric and transitive, we can say that R is an equivalence relation. Now next part of the problem is show that the set of all the points related to a point P which is not origin is the circle passing through P with the center origin. Okay. So see here, you can see this circle. Here we are considering our center O. Now we want to find a set of points which are at the same distance from the origin. So the set of points which are at the same distance from the origin is a circle. That's the definition of circle, right? So through words only we can understand that will be the circle, right? So here set of all the points related to P will have the same distance from the origin as P. Note that here OP equals to OQ is equals to OR. Other points who have same distance from origin as OP will lie in a circle with center O and radius OP, right? So we can say that here all the points related to P is the circle with center O and radius OP. Now question number 12. Show that the relation are defining the set A of all the triangles. Means set A consists only triangles. Okay. Now relation R is defined in such a way that all the triangle T1 and T2 if T1 is similar to T2. When I introduce this concept, then that time only we have discussed this type of example. In that we have discussed about congruence. Okay. Here we have a similar is an equivalence relation. Consider three right angle triangles T1 with side 3, 4, 5, T2 with 5, 12 and 13 and T3 with side 6, 8 and 10. Which triangles among T1, T2 and T3 are related? So that we will discuss later on. First of all, solve the first part of the problem. So I think you must have, all of you have that concept that A is what? A is a set of triangles. Okay. So it doesn't mean that set always contains some numbers. Set can contain anything. It may contain lines, it may contain triangle, it may contain quadrilateral and so on. Okay, so here our set A contains triangle. Now our relation R is defined in such a way, say that we will consider only those pair of triangles which are similar to each other. Okay, so for reflexivity, since every triangle is similar to itself, we can say that triangle T is similar to triangle T. Okay, each and every triangle is similar to itself. So we can say that here TT belongs to R and therefore R is reflexive. If you select any element from your set A, that element will be one triangle and that triangle will always similar to itself. Therefore, this relation is what? Reflexive. Now let us check the symmetricity. Now if triangle T1 is similar to T2, obviously T2 is similar to T1. So this is very simple that if T1 T2 belongs to R, then T2 T1 belongs to R. And in that case R is symmetric. Now for transitivity, if T1 is similar to T2, right? So if triangle XYZ is similar to triangle PQR and triangle PQR is similar to triangle ABC. Okay. So instead of triangle PQR XYZ ABC, here we have written T1, T2 and T3. So if T1 is similar to T2 and T2 is similar to T3, T1 is similar to T3 and therefore the relation is transitive. Since R is reflexive, symmetric and transitive, therefore R is an equivalence relation. Now next part, consider three triangles T1 with side 3, 4, 5. So our first triangle T1 has all the sides what? 3, 4, 5, which is right angle triangle. T2 with side 5, 12, 13, again it is right angle triangle. And T3 with side 6, 8, 10. Which triangles among T1, T2 and T3 are related? Now see, T1, T2 and T3 are related only if they are similar to each other. Okay, so we need to check whether T1 is similar to T2 or T2 is similar to T3 or T1 is similar to T3. Okay, how can we check? They are similar if the ratio of their side is equal. Okay, so T1 has side 3, 4, 5, T2 has 5, 12, 13 and T3 has side 6, 8 and 10. So for triangle T1 and T3, see 3, 4, 5, here we have 6, 8, 8 6, 8 and 10. Okay. So we know that if we multiply 3, 4, 5 by 2, we will get 6, 8, 10. Right. And we can get infinitely many similar triangle to this triangle 3, 4, 5. How? By multiplying with any real number. Either you can take 2, 3, 4 or anything. Okay. So here ratio of their side 3 upon 6 is equals to 4 upon 10 is equals to 5 upon 10 is equals to 1 upon 2. So since ratio of sides is equal, T1 and T3 are similar. Can you say that T1 and T2 are similar? No. What about T2 and T3? No, they are not similar. Why? Because the ratio is going to be different. Okay. Now next question. Question number 30. Show that the relation are defined in the set A of all polygons. As R, P1 and P2 have same number of sides is an equivalence relation. What is the set of all elements in A related to the right angle triangle T with sides 3, 4 and 5? Again this question has two parts. So let us consider the first part. Okay. So P1 and P2 have the same number of sides. If I am saying that P1 has 3 sides, so P2 must have 3 sides. So that means if P1 is triangle, then P2 should be triangle. If P1 is quadrilateral, then P2 should be quadrilateral. If P1 is pentagon, then P2 should be pentagon. Okay. I think you understood this question first. Okay. Now check reflexivity. So P1 and P1 are the same polygon. Okay, so they have the same number of sides and therefore P1 comma P1 belongs to R. Therefore R is reflexive. Now let us check symmetricity. So if P1 and P2 belongs to R, what does it mean if P1 P2 belongs to R? It means that P1 and P2 have the same number of sides and therefore P2 and P1 have the same number of sides. Hence P2 P1 belongs to R. Similarly, you can prove transitivity. So, in short, this relation is what? Equivalence relation. So, let us move on the next part of this question. So, what is the set of all the elements in A related to right angle triangle T with sides 3, 4, 5? Now, see, if A is related to the right angle triangle, okay, now whether the triangle is right angle triangle or it is equilateral triangle or it is isosceles triangle or any triangle, all the triangle have 3 sides. That is general truth, right? So, if we say R is equals to P1, P2, then P1 and P2 have the same number of sides. Now, if P1 is equals to T, then T and P2 are in relation R. That means T and P2 have same number of sides. It means P2 also have how many sides? 3 sides. So, if P2 has 3 sides, we can say that P2 is set of all the triangles. Hence, the set of all elements in A related to triangle T is the set of all the triangles. Let us move on to the next sum. Question number 40. Let L be the set of all the lines in a xy plane and R be the relation in L defined as all the line L1 and L2 where L1 is parallel to L2. So first of all, let us understand the first line. L is what? L be the set of all the lines in a xy plane. So here we are talking about Cartesian plane. And we have the set which contains what? Lines which are in xy plane. Now relation R, so in R out of all those lines there will be infinitely many lines, but we will consider only those lines which are parallel to each other. Okay. So here our question is show that the R is in what? Equivalence relation. And in second part, find the set of all the lines related to the line y equals to 2x plus 4. So that we'll do later on. First of all, let us do the first part. Now see, if L1 is parallel to L2, we can always say that any line is parallel to itself and therefore LL belongs to R. Hence R is reflexive. Now if we consider any line L1 and L2, if L1 is parallel to L2, L2 must be parallel to L1 and therefore if L1 L2 belongs to R, we can say that L2 L1 belongs to R and therefore it is symmetric. Now consider transitivity. So if one line is parallel to other line and that second line is also parallel to third line. So we can always say that first line is parallel to third line. See here, if line L1 is parallel to L2 and L2 is parallel to L3, we can say that L1 is parallel to L3. Hence, L1, L3 belongs to R. So here R is transitive. Okay, so R is an equivalence relation. Now we want to find all the lines which are parallel to the given line. So how to find it? Now we want to find lines which are parallel to y equals to 2x plus 4. Okay. So how to find it? See, in 11th standard we have discussed that family of lines which are parallel to ax plus by plus c equals to 0 is equals to ax plus by plus any other constant. Instead of c, we'll take here other constant. Let us take it as a k. Okay, so if the given line is ax plus by plus c equals to 0, then family of lines which is parallel to the ax plus by plus c equals to 0 will be ax plus by plus k equals to 0. Only constant term will be different. Or we can also say they will have the same slope. Okay. So here equation of line parallel to y equals to 2x plus 4 will be y equals to mx plus c. See, always remember whenever you want to find a equation of parallel lines, ax plus by will be as it is. Only their constant term will change. So here m is the slope of this line, right? Y equals to mx plus b. But if this line is parallel to 2x plus 4, then they must have the same slope. Okay, so we can say that m is equals to 2. Okay, therefore, family of line which is parallel to the y equals to 2x plus c, 2x plus 4 is what? Y equals to 2x plus c, where c belongs to R. Remaining question number 15 and 16 is your homework as they are of MCQ types. In next lecture, we will discuss different types of functions. Thank you.